We're going to be speaking about the idea of paying attention, and this will be an application of the chain rule. So consider an animal that has two food types with possibly different nutritional value. So the nutritional value of one of them will be scaled to be 1. The nutritional value of the other food type will be n times that, so will be denoted by n. So these are nutritional values of each of the two food types. The attention required to find the food types will be x and 1 minus x. We're here assuming that the total amount of attention is fixed, meaning the animal can at best subdivide its attention into two pieces which have to sum up to be a constant that we will scale to be 1. Now the total value of the food that the animal finds, denoted by v of x, is going to be the probability of finding food type 1 based on how much attention is devoted to that task, plus n times the probability of finding food type 2, given that the animal spends the rest of its attention on finding that second food type. The idea is going to be that we'd like to somehow maximize this value. And the question is, how should the animal subdivide its attention in order to do so? We're going to take a specific example just to illustrate the general ideas. In that example, we're going to choose both food types to have the same exact nutritional value, so n and 1 are identical. We're going to take functions p1, which is simply x squared, and we'll take a function p2, which takes its argument and cubes it. So in other words, what we'd like to do is maximize the function x squared plus 1 minus x all cubed. That will be our goal. So we've got the following function that we'd like to optimize. Therefore, when we compute the derivative of the food value in order to find an optimum, we're going to have to use the chain rule on this expression. So the first part, that's easy. The derivative of x squared is just 2x. And now here's where the chain rule comes in. The derivative of this part will be 3 times 1 minus x raised to the power 2 multiplied by the derivative of the inside with respect to x, which is minus 1. In order to optimize then, what we have to do is set this equal to 0 and solve the given equation for x. This is a quadratic equation, and when we solve this, we will find that x is equal to plus or minus root 7 divided by 3. So it appears as though we found an optimum. But let's be a little bit careful here. Let's observe what happens with the second derivative of this function. Let's compute that second derivative right here. What we get is 2 plus 6 times 1 minus x to the power 1. Now notice that for any value of x between 0 and 1, this second derivative is greater than 0. When that's true, we know that the function itself is concave up. So actually the point we've found is not at all an optimum. In fact, it gives us a local minimum, this particular function. Therefore, what we've determined is that in this example, the optimum occurs not at some local maximum, but rather at one of the two endpoints of the domain. So now let's look at this function one more time and examine what happens at the two endpoints, namely when x is 0 and when x is 1. In this case, we get equal value if we pay full attention to food type 1 or to food type 2. These two come out to be precisely the same, and both of these strategies are better than subdividing attention between the two foods.